Today we're going to look at an application of a sinusoidal function. When a weight is suspended from a spring that is mounted from the ceiling, the weight will remain at its equilibrium position unless disturbed. If at a time 0 seconds the weight is pulled down 16 centimeters, it might oscillate as follows. After 1 second it's back at its equilibrium position. After 2 seconds it is 16 centimeters above equilibrium position. After 3 seconds, it's back to its equilibrium position, and after 4 seconds, it is again 16 centimeters below the equilibrium position. Now, if the equilibrium position is actually 100 centimeters above the ground, we want to draw what that weight's position versus the height above the ground after t seconds. And if we take the information up above, we'll find that the function will look much like this. I graphed the time on the horizontal axis with the letter t, and since my graph was going to have its equilibrium, or kind of the resting state of the spring, was going to be at 100 centimeters, I had to have my graph scaled. I chopped the graph so I didn't go all the way down to 0. But I needed to have the spring be able to be 16 centimeters below equilibrium and 16 centimeters above equilibrium. And I know that the spring at time 0 is pulled down to the 16 centimeters below equilibrium position and then released. So after 1 second, it's at equilibrium position. After 2 seconds, it's to the top. And again, I'm having that same pattern that every 1 second it's moving from basically a critical point to the next critical point. Or it's going to take an entire 4-second span of time for it to get through the entire cycle. Therefore, my period on this graph would end up being 4 seconds. Now, in the next part, we want to write an equation for a cosine function, including the units on the constants. And we had previously written an equation on the last video. However, we hadn't put any units because it wasn't in a context. This one will be in a context. So there are actually many ways to write a cosine function to show this model. Here is just one. And remember, we have basically an A, B, a phase shift C, and a vertical shift D that we have to figure out. And so the vertical shift of the graph is going to be the center of the graph. We know that the graph went as low as 84 centimeters. This would be at 84 centimeters. It went as high as 116 centimeters, or 16 centimeters above equilibrium. And so we know if we find the mean of these two, we'll find what the middle of this is, which was the equilibrium position, or 100 centimeters. And we also know that the amplitude is how far it's stretching from the equilibrium position. So I chose to write this as a cosine function that actually does not have a phase shift. I started it at a low. Remember, cosine functions are always going to be starting either at highs or low when we write our model. So if I started at a low, I need to have a coefficient of negative 16, and in the unit of centimeters as the lead coefficient. And then I don't have to have a phase shift in this part. So we have little a determined. Now little b, we have to use our period of our graph. And because the period, or the amount of time it takes to finish one cycle, is 4 seconds, and we know that the period is 2 pi divided by b, that also means that b will equal 2 pi divided by the period. So b can be written as 2 pi over 4 seconds. Now if you leave it in this form unreduced, that's fine. I actually reduced it down when I wrote it over here. Now little c, I'm choosing not to phase shift it, so I didn't have to worry about having a parenthesis and a t minus some type of a phase shift. Although I could phase shift it over here to a high, and I could have this as a positive 16 centimeters cosine of pi over 2 seconds times t minus, and I could phase shift it to this high at 2 seconds. And then we finally have our vertical shift at the end, where the middle of the graph is. So here are two different possibilities for a cosine model. Now if I want to rewrite it, which I will in a second, it's very easy to change this type of a model to a sine function. But in the next part, I'm just showing that my units are in fact working, and I plugged 3 seconds in place of the independent variable. The seconds cancel. I have a radian measure here, and when I take the cosine of this value, I get a number that does not have a unit. It's just a ratio, and I multiply it by centimeters. This technically is a centimeter unit, although it's 0, and plus the 100 centimeters gives me my 100 centimeters. So it's always a good thing to go back and check and make sure that your answers, your equation fits your model just by plugging a point in. And we can see that at 3 seconds we should get 0. If I want to write a sine functions start in middles as far as where the phase shift is. And so here's one example of a function I could use for the sine. A middle occurs at 1 second, 3 seconds, 5 seconds, 7 seconds. I chose to use the first one, the 1 second. So we have our amplitude, and since the graph is rising up from 16 centimeters, or from the 100 centimeter mark at the 1 second mark, we do want this coefficient to be positive. Next page. I verified that my equation was right by plugging in 4 seconds, and you can see how my unit analysis actually worked out well, and I can see that if I look at my graph, that at 4 seconds my sine function does tell me I should be at a position of 84 centimeters, and that's in fact where I'm at. Now I wanted to use my equation to answer the question of when will the weight be 110 centimeters above the ground. So I set my equation equal to 110 centimeters. I chose to use the cosine function, which was the part from part B, and I did my algebra. I'll have to subtract 100 centimeters from both sides and also divide each side by negative 16 centimeters. Now I'm ready to take the inverse cosine. And when I take the inverse cosine, I will find this angle, but I have to remember that inverse cosine, I have angle plus 2 pi n and opposite. And then to finish solving for t, I multiplied both sides by the reciprocal. And this needs to be multiplied through by all those factors. And that gives me my general solution. Now I could use this general solution to find the first 4 times, or the very first time, or the first 10 times. So this is useful in finding any number of solutions I want. Now we can also go through and use our sine function to solve. And the sine function is going to be very similar. I used a different location of having my sine function when I have the weight be at 95 centimeters above the ground. And the only thing we have to remember that will be different about sine is I subtracted the 100 divided by the 16 centimeters, and now I'm ready to inverse sine this ratio to find this angle. And we have to remember that it's angle and supplement. So when I hit inverse sine with my calculator in radians, I got this, and then I have to find its supplement. So pi minus this negative angle gave me this 3.459 plus 2 pi n. And then I had to get rid of these things piecewise. Got rid of the pi over 2 seconds by multiplying by the reciprocal. And that gave me this. And remember, this does need to be distributed through to all of these terms. And then finally, I would add 1 second to each side. And when I add the 1 second, it does not get added to this 4 second n because it has the n attached. And that's my final solution. So we have a couple different ways of basically solving a cosine function and sine function are going to be very similar, except when you actually take the inverse. Sine and supplement, cosine and opposite. And that's it for our spring example.